This is Lesson 2.2, Statistical Data Analysis. We're ready to start looking at how we can use MATLAB for some basic data analysis tasks. First, what is data analysis? Put simply, the field of data analysis aims to understand the trends and relationships in data sets. In this lesson, we explore some of the tools in the MATLAB environment to statistically analyze trends in sets of numbers. Basic statistical analysis includes computing metrics such as the mean and standard deviation of numbers in a data set. More sophisticated analysis includes computing confidence intervals for distribution estimates or performing hypothesis testing. MATLAB has a suite of methods to assist with performing such a wide range of tasks. In this lesson, we'll visit such tools and functions and show how they can be used in MATLAB. Let's get started. Let's start with some basic statistical analysis of our iris data set. Let's examine feature 1 for the first 50 samples of our data set. That gives us a set of 50 floating point numbers in a vector V. Okay. Let's do some basic statistical analysis of this set of numbers. Most commonly, we are interested in questions like, what is the average value or mean of the data set? In MATLAB, we simply do mean of V, and we see MATLAB returns that the mean of this data set is just over 5. What other functions might MATLAB have to perform similar data analysis tasks? Remember, we can always type help function name, and at the bottom of the page there is a See Also section. In the See Also section for mean, we see functions median, STD, which stands for standard deviation, min and max, which stand for the minimum and maximum value of a vector, and mode, which stands for the mode of the vector. We also see var, which would return the variance, and cov is the covariance, which is a metric of variance for multidimensional features. So that function does not apply for our vector v. Let's try out the first set of 1D analysis functions. The median function finds the median value of the data set, which we find to be 5. The standard deviation function will give us the standard deviation, which is 0.35. The max and min functions give us the maximum value and the minimum value in V. This lets us know the range of the data set. And the mode function returns the most frequently appearing value in the data set, which is 5. All of these metrics give us some understanding and intuition about the data set. The functions that find a single value in the input array, like the min and max functions, also optionally return a second output. If 2 outputs are included, the second output provides the index to that value in the array. So for example, if we type vmin I for index is equal to min v, not only do we find the minimum value of 4.3, we find which entry in V corresponds to that minimum value. Using the sort function, we can also sort data in V. Note that after we sort the data, several of the above metrics are easy to find. The minimum value is the first value in V sort. The maximum value is the last value in V sort. The median value is the middle entry in the sorted array. How do we find the middle of the array? Well, for an array that is of length 1, the middle would be entry number 1. For arrays of length 3, the middle would be entry number 2. For arrays of length 5, the middle would be entry 3. Mathematically, this is quantity LV plus 1 divided by 2. So let's try that. Oops, what happened? What is the value of LV plus 1 divided by 2? So we can see that because LV is 50, which is an even number, LV plus 1 divided by 2 is not an integer, and we can't index into VSort at a floating point location. When the length of the array is an even number, such as the length of V being 50, the median is the average of the two central entries at indices 25 and 26. Since both the entries at 25 and 26 have a value of 5, we see the median is 5. Another name for the median is the 50th percentile of the data set. It is called this because it is the value that corresponds to including 50% of the sorted data. We can also evaluate the 25th and 75th percentiles, or any other percentile, by evaluating the appropriate entries in the sorted array. The 25th percentile of V is at the 13th entry of VSort. There are two common metrics to gain intuition about how spread the data are around the mean or median. One is the standard deviation from the mean, and the other is the range from the 25th to the 75th percentile of the data set. The latter measurement tends to be more useful for data that are non-normal. In addition to using MATLAB's functions to obtain the values for these statistical quantities for a data set, we can also visualize a lot of this information easily in MATLAB. One way to do this is using box plots. We can open a new figure window and then use the box plot function with the data set as input. In the figure, the box plot shows the median value of the data set with the red line. The range of the data from the 25th to 75th percentiles is shown with the blue rectangle, and the black whiskers show the total range of the data, with the potential exception of outliers, which would be shown separately with red pluses if any were detected, which they are not in this data set. This plot can help us visually understand the data. If we have multiple data sets, we can use the box plot function to show both of them. For example, if we define V2 to be the value of the first feature for the second species of iris, which are entries 51 to 100 in the data set, then we can make box plots of both vectors by providing them as columns of a matrix into the input for box plot. This lets us see these two datasets side by side. We can easily see that it looks like these two datasets have some overlap in numbers, but generally have most values falling in different ranges, with the 25th to 75th percentile ranges for the two datasets having no overlap. We will see more about data visualization in the next lesson. This brings us to the concept of statistical hypothesis testing. Oftentimes, we want to ask the question, is one dataset different from another dataset? For example, is V different from V2? While this general question is often quite pertinent, it is not very specific. Different how? In statistics, hypothesis tests exist to answer very specific questions about how samples from one process may be different from another under very specific conditions. If we assume the means of the two processes from which V and V2 are sampled are normally distributed, we can test whether the mean of process 1 is statistically significantly different from the mean of process 2 using one of the most common statistical hypothesis tests called Student's t-test. The t-test was developed by William Gossett under the pseudonym Student. He was a chemical engineer working at the Guinness Brewery in Dublin, Ireland. He wanted a way to test whether different batches of stout were leading to different results. And little did he know that he had created what would become the most widely used hypothesis test in all scientific studies since. In MATLAB, this test is available in the function t-test2. This function generates a so-called p-value, which represents the probability that we are incorrect if we conclude that the mean of the distributions v and v2 are drawn from are not equal. In the vast majority of applications of t-tests, a threshold of p less than 0.05 is determined as the threshold for concluding a significant difference exists between the two distributions. Thus, a t-test returns h is equal to 1 if the p-value is less than 0.05, which means we reject the null hypothesis that the means of the distributions for v and v2 are equal. Otherwise, it returns a 0, h is equal to 0, if p is greater than 0.05, and we cannot reject the null hypothesis that v and v2 are drawn from distributions with equal means. In this particular case, we find h is equal to 1 with a p-value much lower than 0.05. So we conclude the two datasets are drawn from distributions with significantly different means. There are a suite of hypothesis tests built into MATLAB, each of which tests various hypotheses, and each is intended for use for inputs that satisfy certain conditions or have different distributions. Visit MATLAB's hypothesis testing help page for more information about functions that are available. A word of caution is warranted about statistical analyses. While the algorithms provided by MATLAB are quite easy to implement and use, often the most difficult part is determining which method or test is appropriate for a given dataset or hypothesis. Further, how to responsibly interpret the results also requires statistics expertise. There are no MATLAB functions to help with these high-level decisions. This is your responsibility as the programmer. If you are not familiar with the technical limitations of a t-test or how to responsibly interpret its results, the use of such tools could be dangerous. For a more thorough introduction about such statistical methods, how to use them, and how to interpret them, I refer you to further reading in the text shown here geared towards engineers and scientists. If you have followed this lesson and completed the accompanying exercises, you now have an understanding of how to perform basic statistical data analysis in MATLAB.